rubber band has enough energy to smack you in the arm and cause a sting. Ouch! You must be wondering, what is the relationship between a stretched rubber band and when it's at rest, and how much energy it has hold? In our experiment, we believe that the potential energy the rubber band has stored can also reflect the rubber band's elasticity, which is related to distance of the object flight after it's being released. We can determine the potential energy of an unknown object by how far of a distance the object was shot, and using a calibration curve of several materials with their known elasticity coefficient, we can also calculate the elasticity of the unknown object.
As Marie said, the goal of this experiment was to create a calibration curve so we could find the spring constant of household objects. This meant we needed to build a slingshot that could both shoot vertically and horizontally while also being able to use rubber bands and household objects. Our team went right to work to build a slingshot that could be both level vertically and horizontally to shoot the ball in only the X component and the Y component, while also being consistent in the amount that the rubber band was stretched. Our team finally was able to produce a slingshot. 2 vertical nails 4 inches apart on a 1.2 meter board with a mark 3 inches down, dead center between the nails at 2 inches apart from each, was made. This ensured that the board could be leveled vertically on one side, horizontal on the other side, and the bands were evenly stretched at the 4-inch mark here and the 3-inch mark here to ensure that each shot was consistent. When firing, the ball was brought down so that the very bottom was tangent to this marker line, so that each time the ball was brought down the same amount. The setup for the launch was quite easy. First, the plank was leveled, then the band was pulled back 3 inches and fire. The ball was released. Horizontally, the board was put on a level surface, pulled back, and fired. A video of the flight was recorded on an iPhone and then imported to Tracker for analysis. The coordinate axes for the analysis was placed in the middle of the board, right where the board met the table was propped up against. This ensured that the height of the ball was consistent on each tracked video. A similar process was used for the horizontal shot to measure the coefficient of friction. The coordinate axis was placed on the very tip of the 1.2 meter board to keep the distance and the X direction consistent. When the ball was shot, a point mass was used to model the motion. When the ball came to a complete stop was when the tracking ended. At this complete stop was noted as the distance traveled by the ball.
So, what were the results of this experiment? As you know, we did 4 trials to create our calibration curve using 4 different rubber bands and ordered 1 through 4 in order of trials. The max heights were 2.59 meters, 4.56 meters, 2.74 meters, and 3.34 meters. And then using the formula to calculate spring constants, we found respectively, again, 1 through 4 in order, that their spring constants were 26.26 newtons per meter, 46.14 newtons per meter, 27.74 newtons per meter, and 33.081 newtons per meter. So, when graphed as a function of max height over spring constant in newtons per meters, we found the r squared value to be equal to exactly 1, which means that it is a perfect linear relationship between max height and spring constant. And also, the slope and the equation of the line was 0.0987x with no y-intercept, implying that if an object had no spring constant, it would not be able to reach any height using an elastic pull. So what does this tell us? What this tells us is that now, using this calibration curve, especially with such a high r squared value, we can take any spring constant or any max height and rearrange the equation to find its spring constant. So our unknown spring constant, or our unknown max height rather, was 1.03 meters. So all we need to do now, because there was no y-intercept, is divide 1.03 meters by 0.0987, or the slope, and you get the spring constant of 10.434 newtons per meter. And that is true for any object that is able to reach a height. You can just divide it by the slope of the line, 0.0987, and find the spring constant. Okay, so what was the dominant error in this experiment? After doing our analysis, we found that the dominant error in this experiment would most likely be the tracking software tracker. And the reason for this is due to frames per second in video. So this experiment was filmed at 30 frames per second, which means that there were only 30 instances per second in which the position of the rubber band was actually captured and thus able to be truly known. That means that in between any of these frames, while you can make an educated guess, you can't actually know exactly where the object was because obviously it was never captured. This uncertainty of the object's position in between frames becomes especially apparent when you are trying to deduce the max height, as you can never know for certain whether or not your observed max height, which happened and was captured in a frame, was close to the real max height that most likely happened out of frame. So that's what creates the error. And in an ideal case, that being the case that creates the most error, an object would travel upward for half a frame and then travel downward for half a frame, meaning that its real max height was exactly halfway in between two frames. So what does this mean? And why is it? The reason that half a frame gives the most error is because obviously halfway gives the most amount of time on either side where it is unknown where the object is moving. And to finalize this calculation, all you need to do is take the velocity from the frame previous to the observed max height, and we assume this velocity to be continue throughout the entire duration of the frame. And then convert that velocity from meters per second to meters per half a frame. And in this case, half a frame, if it was shot at 30 FPS, would be 1/60th of a second. So the final expression for the dominant error is, as I said, the velocity of a frame directly before the object reached its max height multiplied by 1/60th, or the duration of half a frame in seconds.
So here is the question. What can we do to refine the experiment and improve our measurement? We do have to consider the air resistant in real life situations comparing to the ideal scenario, which would be a vacuum environment. Air forces can shift the position of the object shot and add distance to the x-axis direction, and therefore the results might be varied and not accurate. So if we can conduct the experiment in a vacuum environment, the result will be more accurate. As we are low budget students, of course, we can only afford equipment to a certain quality. The result will be more conclusive if we can manufacture the rubber bands with the exact elasticity coefficient. A better quality of the camera can definitely capture more frames in the videos, which could yield a more detailed and accurate data set. The degree of how much of the rubber band was stretched could also be biased based on different individual strength and their location. If we have more people to repeat these experiments, we can definitely find more applicable calibration curves to the unknown object in more general real-life situations.
The data produced from our test create a calibration curve that is applicable to finding the elasticity of household objects, as we showed with the hairband. You could test the elasticity of this Hamilton mask or this stretchy shoelace, all from creating a slingshot identical to this and shooting a ball into the air, and then plotting that height of that shot on our extrapolated calibration curve. As we've shown, knowing the elasticity of a band is very useful. We were able to calculate the coefficient of friction of a parking lot in East Lyme, Connecticut, from knowing the amount of energy that this band would produce. You could also find the grade of surfaces. If you would put this slingshot on an unlevel surface and shoot it up, you could find out how much force gravity is pushing on it compared to a level surface. You could also test the surface tension of water. You could find a liquid that has very little surface tension and water and shoot a band with a known elasticity into that and see the difference between the two. So knowing the elasticity of the band is very vital in doing experiments with changes in energy.